now let's talk about stability, right, of critical points. So we say that a critical point of a system of differential equations, well, in this case it is the critical point at the origin, but generally speaking for nonlinear systems it may be some other critical point, but in any case, so if it is asymptotically stable, means that all trajectories converge to the origin, are stable if they just go in circles, and unstable if all or almost all trajectories they go away from the origin. Now I suggest that you come up with a rigorous definition of this that could be applied to not necessarily linear systems of ordinary differential equations, or just Google the right definition. So we have almost proved the following theorem. So if we have a system, a linear system with constant matrix of coefficients A, then the critical point at the origin is asymptotically stable if and only if the real part of every eigenvalue is negative, stable if it is non-positive, and unstable if at least one eigenvalue has a positive real part. Now notice that I use the word almost. The reason why this is almost is because we actually only proved it for diagonalizable matrices. But the theorem is still true for non-diagonalizable matrices. It's just that it's a bit trickier to check it. But anyway, the theorem is correct. So if you are very interested in the subject, I suggest that you just read the textbook about non-diagonalizable matrices and see how it is done in case of non-diagonalizable matrices. All right, now let's look at a few examples. So here is my first example, this stable unstable spiral point or spiral source. So this happens when trajectories are spirals that drift away from the origin. So in other words, it happens when the determinant of the matrix is positive, the trace is also positive, and the discriminant is negative. Well, then the magnitude of the determinant, it kind of shows how fast these spirals rotate, and the magnitude of the trace, it shows how quickly they drift away from the origin. Well, these are just two examples, and again, to be able to accurately sketch spiral sources by hand, we would have to kind of quantify the skewness and the speed of rotation, but we are not going to do it. I don't think it's very necessary to do it, but yeah. So let's just look at some more examples. Then spiral sink is exactly the opposite picture, when spirals drift or tend to converge towards the origin, right? So it happens when the determinant of the matrix is still positive. Of course, negative determinant is only possible when the critical point is a saddle point, right? So all other cases are when the determinant is positive, right? So now the trace is negative, and the discriminant is again negative because to have complex eigenvalues. All right, so it is again. So this is a spiral sink, and so here the magnitude of the trace of A, it tells us how quickly spirals approach the origin, and the magnitude of the determinant A, it kind of shows how fast the spirals rotate. Okay, well, in a way. So these are two more examples. Well, and finally we have a center. So when the center happens when the trace of the matrix is exactly 0, and the determinant has to be still positive. Of course, if the trace is 0 and determinant positive, then the discriminant is automatically negative, because the discriminant is trace squared minus 4 times the determinant, so it's automatically negative. so the center is stable but not asymptotically stable. Now centers can also be kind of skewed, right? So then this is how it looks like, but then I don't want to get into details, so here is a little quiz for you. That's all I'm going to say about spiral points and centers.